Good morning, dear students. This is Dr. Sabiha Khan, Department of Microbiology, Barakpur Rashtraguru Surendranath College, Kolkata. Today, I will be giving a lecture on the basic concepts of thermodynamics. So, what do we mean by thermodynamics? Before I start up, I would like to mention that thermodynamics is a very important branch of physical chemistry, where thermodynamics can be defined as the science of energy. That means the biological processes, whatever is going on, in which form, in which mode, and whether the process is going to happen or not, we will understand if we understand the basic concepts and the laws of thermodynamics. So we can say that it deals with the most basic processes occurring in nature. Now this word thermodynamics, it is actually made up of two Greek words, where, as we all know, thermo means heat or hot and dynamics means movement or motion, or we can say study of matter in motion. Now basically when we look upon thermodynamics, it has been found out that there are some basic laws that have been framed on the basis of which all the various biological life processes, they are assessed or dependent on these laws. So what are these laws? I would like to give a very brief introduction about the various laws of thermodynamics, and then I would be going into the details of the different thermodynamic parameters, the zeroth law, first law and the second law, which is included in your syllabus. So the different laws of thermodynamics are zeroth law, first law, the second law of thermodynamics and the third law of thermodynamics, and this is what we deal with in this portion of thermodynamics. Now the zeroth law states that if two systems are both in equilibrium, thermal equilibrium, with a third one, then they are in thermal equilibrium with each other. And what does the first law state? The first law of thermodynamics states the increase in internal energy of a closed system is equal to the heat supplied to the system minus work done by it. We will be going into more details of this law. And the second law of thermodynamics says that the entropy of an isolated system not only not in thermal equilibrium, almost always increases. That means the entropy of the universe always tends towards maximum. The isolated systems continuously evolve towards the thermal equilibrium, the state of maximum entropy of the system. More simply, we can say that, as I mentioned earlier, the entropy of the universe or the world only increases and it never decreases. Now finally coming to the third law, which states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. However, here in your syllabus we are not concerned with the third law because you have till the second law of thermodynamics, and we will be concentrating on the first lecture till the first law of thermodynamics. Now before we go into the deeper of how and what is the first law of thermodynamics, I would like to mention some of the very important parameters that are very much related to this world of thermodynamics. And whenever we are considering the different biological reactions, whether it be the lab reactions or the natural life processes, we will be always coming around with the different topics such as these. So I would like to mention the definition and the meaning of what these thermodynamic parameters are. Now system. System is what? System means, as it's written here, a quantity of matter or a region in space chosen for study. That means the system means the particular thing or the subject that I am studying on, or suppose it is me who is giving a lecture right now. So I am the system, and the system minus the rest of the place or the surrounding, that is the portion which is included outside the system, known as the surrounding, as you can see in this diagram. Now boundary is something that can be real or imaginary, because it is something which is separating the system from the surrounding, and as we all know, the system with the surrounding together makes the universe. Now there are basically three types of systems: isolated, closed and open system. So what are these? Isolated. Isolated system is such a kind of a system where there is no exchange of mass or energy, and none of these can cross the selected boundary. That means the mass or energy cannot enter, as well as the mass and energy of the system cannot go outside into the surrounding. And what is the best example of an isolated system? As we all know, that the thermos flask or a well insulated thermos bottle, where we can keep any liquid or anything in a closed system and there is no exchange of mass and energy. So we call such a system as an isolated system. Now coming up to the next system, that is the closed system. As you can see the diagram on the left hand side, we can understand that there is no exchange of mass. See, this is written NO, no on mass, whereas there is only exchange of energy. Okay, and such a system is known as a closed system. That means a system where only exchange of energy can take place between the system and the surrounding through the selected boundary is called a closed system, whereas there is no exchange of mass. So there are plenty and numerous examples of closed system. I have given a single example over here, and as you can see, it is a tightly capped cup of coffee, where what happens if I take a cup of hot coffee, continuously the temperature will start decreasing of the coffee, and slowly there will be a release of energy and the coffee will cool down, whereas after 1 hour or 2 hours I will see there is no change in the mass or no exchange of mass has taken place. So such a system can be called as a closed system. Now coming up to the third system, that is the open system. As you can see in the diagram left hand side, open system, that means it's open to all. So basically what we are considering is that there has to be an exchange process of mass and energy. That is what we are concerned. And in an open system there is an exchange and it is allowed. There is a mass exchange and as well as there is a exchange of energy as well. So we can call a system to be open if there is an exchange of both mass and energy that can cross the selected boundary. And there are numerous examples of such open systems as well. And taking an example of an open cup of coffee or an open cup of tea or whatever, it is an open system because gradually there is a release of energy. If it is hot, it will cool down, the surrounding will gain more temperature, and as a result of evaporation also the volume will also decrease. So there is an exchange of mass and energy, and such a system is called an open system. Now we have learned what are systems, what are the different kinds of systems. Together with knowing the different kinds of system, we also need to know what are the properties of a system. That means we need to know what is the characteristic property of the system. Now basically it has been found out that this system, properties of this system can be of two types, intensive or extensive. Now what is this intensive? Intensive systems are those that are independent of the amount of mass. That means, let's take an example of temperature. Suppose I have two conical flasks where the temperature of suppose 100 ml of hot water is 100 degrees centigrade. Now I transfer a small volume of the same hot water at 100 degrees centigrade into another container or another conical flask. So depending upon the mass or if there is any change in volume, the temperature is not changing, so it is remaining constant. Similarly, if I consider the pressure also, if I take a small amount of gas into a piston and the pressure is maintained, and if I decrease the volume, the pressure that is maintained will remain the same. So, these are some of the properties of the system where the thermodynamic parameters like temperature, pressure, density, they remain unchanged, and that is they are independent upon the mass of the system, and thus we call those systems as the intensive systems. And coming up to the extensive ones are those systems that are very much dependent on the mass. Let us take an example of the mass itself, the volume, the energy, the enthalpy. So, if I take 100 ml of hot boiling water into a conical and then I divide it and separate it into 50 and 50, so the volume is changing. So, these are totally dependent on the mass of the system. So, this becomes an extensive property. Now, coming up to the specific properties, what are these? The ratio of any extensive property of a system to that of the mass of the system is called an average specific value of the property, and that is also known as the intensive property. So, if I write down what is the specific volume, it is given here in the formula. From there I can find out the internal energy and the total energy. Now, there are other properties or other important parameters that we also need to know, that is the state, the equilibrium processes. So, what do we mean by state? A set of properties that describes the condition of the system. That means, suppose I take an example of the mass or the temperature or volume, anything you can take, and the different surrounding phenomena that are describing that what will be the temperature of a particular amount of liquid or any other thing is known as the state of a system. And coming up to the equilibrium, you all must be knowing that thermodynamic equilibrium is what? Thermodynamic equilibrium or any kind of equilibrium is achieved only when the reactant side or the rate of the forward reaction becomes equal to the rate of the backward reaction. That means the same amount of product is forming as the same amount of the reactant side is remaining. That is what we mean by an equilibrium. And this thermodynamic equilibrium, there are different kinds of thermodynamic equilibrium like the thermal equilibrium, the mechanical equilibrium, the phase equilibrium and the chemical equilibriums. Okay. Now, coming up to the different thermodynamic processes, why we need to know? Because the moment we will be considering different kinds of reactions, whether it is the natural reaction or it is a lab made reaction, there are some specific processes that we need to understand and that we need to maintain. So, depending upon those, we need to know what are the different types of thermodynamic processes that are happening in those thermodynamic reactions. So, what are these? These are the cyclic processes, reversible processes, irreversible processes, adiabatic processes, isentropic processes, polytropic processes, throttling processes. Okay? So, what are these? As the name suggests, the cyclic process, that means the point from where it starts, it will return to the same point. That means it is completing a cycle. So, when a system in a given initial state goes through various processes, no matter how many different infinitesimal small steps is it undergoing, and finally it is returning to its initial state. So, the system we say has undergone or completed a cycle, so we call such a process as a cyclic process. Okay? Now, coming up to the reversible process. What is this reversible process? It is defined as the name suggests. Reversible means it will revert back to the original condition. So, it is defined as a process that once having taken place, it can be reverted back. So, in doing so, it will leave no change in the system or the boundary. So, suppose A is converting to B and B is converting to C. Now, if the process is an entirely reversible process, C will convert into B and B will convert into A following the same steps under the same conditions, and then only we can call such a process as a reversible process. Now, coming up to the irreversible process, this is a process that cannot return to its original initial condition. So, both the system and the surrounding, in this considering both the system and the surrounding, they will never revert back to their original condition. So, if A is converting to B and then to C, it will never revert back to A again. Now, adiabatic process. What is this adiabatic? Adiabatic means there is no heat transfer or heat exchange is constant. There is no change of heat. So, such a process has no heat transfer into or out of the system. So, it can be considered as a perfectly insulated system where there is no exchange of heat energy. Now, isentropic process, it is this process where the entropy of the fluid remains constant. We will be coming into this topic of entropy when we are going to deal with the second law of thermodynamics. So, I will not be emphasizing much on this particular point right at this point, and we will be dealing with it later on. Now, coming up to the polytropic process, when a gas undergoes a reversible process in which there is heat transfer, it is represented in a straight line, and we can write it in this form like PV to the power n is constant. And coming up to the last thermodynamic process, that is the throttling process. It is a process in which there is no change in enthalpy or H. We usually denote with H. We will be coming up to this later on also. So, whenever there is no change in enthalpy, there is no work done and the process is said to be adiabatic. Now, coming up to the thermodynamic equilibriums. So, as I said, basically we will be dealing up with the three kinds of equilibriums. There can be a thermal equilibrium where the equilibrium is achieved in such a condition that the temperature is maintained same. So, there is a constant temperature. If the system is attaining a mechanical equilibrium, there has to be an unbalanced force. This unbalanced force should be totally absent. That means there should be change in pressure. And if we are coming into the chemical equilibrium means that no chemical reaction, it actually seems that no chemical reaction is actually taking place or mass transfer is taking place, but it is actually a kind of a dynamic chemical equilibrium where the rate of forward reaction and the rate of backward reaction actually remains same, and that is why it seems that there is no chemical reaction and mass transfer. Now, as we are going deeper into the branch or the world of thermodynamics, we would also like to know the different other functions of thermodynamics. Okay. Now, basically here we will be discussing on the thermodynamic functions, and there are two most important thermodynamic functions. First is the path function and second is the point function. And as we will be dealing with the different kinds of reactions, we will be dealing with the different situations where some parameters are path functions, some parameters are point functions. Now, what are these? Path function depends on history of the system, that is the background of the system, that is the nature of the system, that is that whether the system has arrived at a final point and what is the path it is following. That means it is path dependent. So, we can call those systems that are very much or whose value is magnitude is very much dependent on path functions or dependent on the kind of path it has followed in the due course of time while attaining its final form are known as path functions. So, there are numerous examples as well. The commonest one that we are going to deal with in thermodynamics are the work and the heat, and you must remember these two important parameters are very much path dependent. So, work and heat are the path functions. Now coming up to the point function. Point function is what? It is just the reverse or the opposite of path function. So if path functions are those that are dependent on the path or the kind of path that it has followed, point functions are those parameters that are totally independent of what kind of path the system has followed. That means it is not dependent on its background, on its nature, on its history. It only depends on the state of the system. That I have already mentioned. By now you all be knowing, or you all have understood what do we mean by the state of the system. We have also known what are the examples of the state of the systems, and those state of the systems are nothing but point functions. For example, temperature, pressure, density, mass, volume, enthalpy, entropy, internal energy. So you can see there are mostly these numerous parameters are all the point functions that are independent of the path. So it is easier for you to remember or learn that what are the point functions, and majority ones are the point functions, and only the two most important ones, that is the work and heat, are the path functions. Now coming up to the zeroth law. Before this zeroth law was framed, actually it was the first law of thermodynamics that was framed earlier, and after the framing of first law, it was found out that there were some preliminary basic fundamentals that needs to be framed in the form of a law, and thus it was named as zeroth law. So what is this law? If two thermodynamic systems are each in equilibrium with a third body, that means suppose we have A, B and C. So coming up to this zeroth law, what it states, if two thermodynamic systems are each in thermal equilibrium with a third body, that means suppose we have three systems A, B and C, okay, and each of them are in thermal equilibrium with a third body, that means A is in equilibrium with C and B is also in equilibrium with C, then they are in equilibrium with each other. That means then A and B will also be in equilibrium with each other. Now what happens when we keep two systems in contact with each other? So whenever we are keeping two systems in contact with each other, there will be definitely a net exchange of energy. There will be if one body is hot, another is cool, there will be an exchange of energy in such a manner that one is going to get cooled and the other is going to get hot, and finally the temperature becomes same, or it comes in thermal equilibrium. So there will be a net exchange of energy between them unless and until they are in thermal equilibrium, as I mentioned. That is the state of having equal temperature. This is what it deals with. So no matter what is the difference in temperature between the bodies, if two of them are in equilibrium with each other, then definitely they will be in equilibrium with the third body. Now although this concept of thermodynamics is very much fundamental, they need to be stated explicitly and this was not widely perceived until the first third of the 20th century, and long after the first three principles were already widely in use, and then only this third zeroth law was framed. That is why it has been named as zeroth law. So it was first the first law that was framed, then the second law, then the third law, and then it was found out that this there was a very much urgent requirement for explaining this phenomenon of thermal equilibrium between three different states, and that is why it has been named as zeroth law. As I mentioned everything, if you can concentrate upon this particular diagram, we can see object 1, which is a thermometer, object 2 and the another object, that is the third system, object 3. So when two objects are separately in thermodynamic equilibrium with a third object, so they have to be separately in thermodynamic equilibrium. then there's no need of linking in between them. So finally they will achieve an equilibrium and they will be in equilibrium with each other. Now I am coming into the first law of thermodynamics. You all are very much aware with this particular equation, that is delta U is equal to Q minus W. And whenever we speak of the first law of thermodynamics, what we remember basically is nothing but this particular equation. Now what is this U? U is the internal energy. If delta is put in before this, that means the change in the internal energy, and as it is written given by the arrow, that is delta U refers to the increase in internal energy. W is nothing, W is the work done. Now there are two conventions which I would like to mention and keep it very clear to you, because most of the students, they get confused that whether the work done will carry a negative sign or a positive sign. I will be coming into that so that it helps you to clear these arguments and confusions. So here the formula or the equation is written as Q minus W, because the work done is by the system. So always remember, whenever there are two options or there are two chances, either the work will be done by the system or the work will be done on the system. So when the work is done by the system, then it is the system is losing energy and it is positive on the system. I'm sorry, when the work will be done on the system, it will lose energy and it will be positive, and when the work will be done by the system, it will be negative and the system is gaining energy. Now if you look into the two conventions, there are basically two most widely accepted conventions. One is Survey's notation and one is the common one, the Jewett notation, where if we consider the work done by a gas, then we can say that if the work is done by the gas, that is by the system, internal energy is denoted by delta U or the U. So the equation will come up to be delta U is equal to Q minus W. And if the work is done on the system, that means the work is being done on the system, then the internal energy, if I refer it as E, so the work done will basically change into positive. So you can also write as delta E is equal to Q plus W, or you can also write it as delta U is equal to Q plus W. There are numerous books that follow the convention of writing delta E with respect to the internal energy, whereas there are many books which refer internal energy with delta U. However, the matter is same in both. Now let's understand it in a more clearer aspect if we look into these diagrams A, B and C. Let's concentrate on the first diagram, A. Now what happens? More heat is added to a system than the system is doing work. So what will happen? We are adding an amount of heat Q, which is equivalent to the magnitude of 150 joules into the system. Now as 150 joules of heat is added, so the temperature of the system is increasing, and as the temperature of the system will be increased, it will perform a work which will be equal to nearly 100 joules. So finally if we calculate the delta U, it will come up to 50 joules. Basically if you look deeper into this first law, you will find out that it is nothing but it actually deals with the law of conservation of energy. So the total energy of the system, as we all know, it remains constant. Either one form of energy will always change into the another form, and finally the total form of the energy is constant, and that is what we mean by the law of conservation of energy, which actually the first law deals with. Now coming up into the second part or the second diagram, that is if more heat flows out of the system. So here it is an exothermic process. The system is liberating energy, the heat. So Q is equal to minus 150. If the system is taking heat, it is an endothermic process. It is denoted with positive sign. So it's written in the first diagram A as plus 150 joule. And if the system is releasing heat, so it is an exothermic process. So the heat the Q the value or the magnitude is written as minus 150 joules. And here it has been found out that the work that is being done is also negative. That means the work is being done by the system. So whenever there is a liberation of energy, heat energy from the system, so if the system is losing energy, the work will be done by the system. So work is negative here. Please keep this point in your mind and keep it very clear. So delta U is equal to Q minus W. So if we calculate the internal energy change, there will be a decrease in the internal energy that comes out to the value or a magnitude of minus 50 joules. Now coming up to the third situation where heat is added to the system that equals the work done by the system. That means the amount of Q that is introduced inside the system and the amount of work that is done on the system is same. So if Q is equal to 150 joules, work is also found out to be equal to 150 joules. And in such a situation, we see that there is no change in the internal energy, that is, it remains constant, or we can say it is 0. So these are the three most important conditions that you need to keep in mind. No need of confusing of whether W will be positive or negative. I think by this time you have learnt that when will W will be negative, when will W will be positive, and depending upon this you will be getting numerous mathematical problems where you have to find out work or Q giving proper conventions, the signs. So summing up them all together, what happens if there is expansion, heat is entering, expansion, work done is greater than 0. Heat is going out, compression, work done is less than 0. Now coming up to the spontaneous process. Now we have nearly done a major part or understood a major part of first law of thermodynamics. Now slowly and slowly I will be taking you up towards the second law. Before understanding the second law, we need to understand certain phenomena like the spontaneous process, the reversible process and the irreversible processes. And then I will be taking you towards understanding the entropy, the enthalpy, the free energy, and finally might be in my next lecture, not in this, we will be dealing with what is the second law of thermodynamics and what are its practical applications in our day-to-day life. So now I will be talking on spontaneous process. What is this? Any process that is occurring naturally without the aid of any external help, or we can say spontaneous processes are those that can proceed without any outside intervention. Let me give you a very common and a beautiful example. Here, although we have given a diagram, I will be explaining that as well. Suppose I want to throw a glass of water upwards in an upward direction. Will I be able to throw that? No. The moment I throw a glass of water up on the sky, what will happen? The water will spontaneously fall down, and so this falling of water is always from a higher position to a lower position, and this is a very much spontaneous process. Okay, now let's take an example of this diagram. What has been shown here? There is a gas in the vessel B, and there is a small controller, and another vessel A is evacuated. Okay. Now if we open the valve, what will happen? The gas which is having containing the vessel B, containing the gas, slowly and slowly it will release that gas from vessel B to vessel A, and finally it will keep on happening. Finally they both are achieving the same pressure. Okay. So the gas in vessel B will spontaneously effuse into vessel A, but once the gas is equal in both the vessels, it will not spontaneously go back into the vessel B again. That means it will not go back to the initial condition, and that is what we mean by a spontaneous process. So, if I want to sum up, I can also say that spontaneous processes are those processes that are happening naturally, that cannot be reverted back. So, I can also say that spontaneous processes are mostly irreversible, naturally occurring processes, and just believe my words, they all are happening or undergoing, obeying the laws of thermodynamics, and that is what we call it as they are very much thermodynamically favorable. Okay. Now, let us take another example. Here you can see a small nail, iron nail that has been left on its own under the atmosphere. After a certain time, what do we observe? It is the natural tendency under the presence of moisture and oxygen, this nail gets converted into rusting, or it gets rusted. Now, if I want to revert back in its original condition, I need to treat it with some kind of an acid. That means artificially I have to treat it so that it can revert back. But naturally, this rusted iron can never go back to its original form. So, the processes that are spontaneous usually occur in one direction. That is what I mentioned as mostly irreversible, and are non-spontaneous in the reverse direction. So, the processes that are spontaneous at one temperature may not be non-spontaneous at other temperature. Above 0 degree centigrade, it is spontaneous for ice to melt, but below 0 degree centigrade, the reverse process is a spontaneous one. So, there are numerous examples of spontaneous processes. When we will be going into the second law of thermodynamics, its explanation, its relation on our practical life, we will be dealing more with the spontaneous processes. Now, I am coming up to the last part of today's lecture, that is the reversible process, and simultaneously I will be also talking about what is the difference between a reversible and an irreversible process. With this, I would be ending up my lecture today, and in my next lecture, I will be continuing up with these topics, going into the entropy, enthalpy, free energy, and the practical applications of the second law of thermodynamics. Now, what is this reversible process? In a reversible process, the system changes in such a way that the system and the surroundings can be put back in their original states by exactly reversing the process. That means, if A has converted to B and B to C and C to D, if it is a reversible process, then D, the moment D wants to convert in A, it has to back or revert the entire process, follow the same conditions. If it is forming any small intermediates, it has to form those intermediates at the same time in the same amount, and then only we can call such a process as a reversible process. So, ideally, if you think that reversible processes are really very much needs to be happened in a very controlled atmosphere. So, this can never happen naturally. So, in a reversible processes, so if I differentiate it with an irreversible processes, obviously irreversible process is totally different. In an irreversible process, the finally formed product will never revert back into its original one, and it will never maintain those original steps that the reversible process is actually maintaining. So, in a reversible process, the changes are infinitesimally small in a reversible process, and it takes a lot of time. So, we can differentiate it in this way with the irreversible process, that a reversible process takes place in infinitesimally small steps, and it is a slow process, whereas irreversible process does not need always to undergo very, very small steps, and it occurs in a very fast rate. Now, here is the irreversible process. As I have already explained, these processes cannot be undone by exactly reversing the change to the system. all the spontaneous processes are irreversible. All the real processes are irreversible, and believe my words that all the experiments and all the data also suggest that all the spontaneous process that are irreversible are actually thermodynamically favorable too. So, they are actually going by obeying their laws of thermodynamics. So, I will be concluding my first lecture into till these processes only, and in my next lecture we will be going further into the details of second law of thermodynamics and its practical applications. Thank you very much.